This is a critique of the failure of Poisson modeling by Sawyer West. This critique focuses on a paper published in 1995 by Vern Paxson and Sally Floyd about the failure of Poisson modeling in wide area traffic. Models of the paper will be shown throughout the presentation. The left picture is Vern Paxson, and the right is Sally Floyd. This model fails because two different types of network traffic may exhibit different traffic patterns. A pattern may be, for example, some sort of bursty traffic, some self-similar traffic, and some sort of traffic dominated by user activity. The Poisson process fails to model these different types of traffic because it does not make the proper assumptions. The assumptions made from the Poisson model is that we know the average time for an event to occur, but predicting the time of any given event is impossible. In this paper, new models for telnet traffic, multiplex TCP traffic, and all protocol traffic were provided, and it was also shown that FTP traffic was not Poisson. Telnet traffic is modeled well by parameterizing originator traffic by hourly connection arrival, since telnet traffic is heavily influenced by the business work cycle. Traffic may not be as high around noon during lunch than during 3 p.m. work crunch. Additionally, there may be very little traffic at all around 3 in the morning. Since Poisson assumes the average time between arrivals is a known constant, it fails to capture the difference between traffic at 3 in the morning and 3 in the afternoon. Multiplex TCP and all protocol traffic can be modeled well with a self-similar model. Self-similarity in a network traffic model is a lot like self-similarity in a tree. Every tree sprouts branches which look vaguely like the tree itself. Since the tree at smaller scales looks like the same as the tree at full scale, we say this tree is self-similar. Therefore, any network traffic which appears to show self-similar patterns on small scales and large scales is called self-similar. Poisson fails to model this type of traffic for the same reason it fails to model telnet traffic. Since Poisson assumes the average time between arrivals is a constant, the similarity in structures at small scales and large scales is disregarded. Without accurate models, computer scientists were faced with a variety of different network problems. Bandwidth was being wasted when traffic was lower than a model predicts, and bandwidth had to be quickly reallocated if there was an unexpected burst that exceeds the model's expectations. The authors claim that the only user session rivals are Poisson, and different techniques are better suited for modeling other traffics. To test their claims, multiple models were put to the test against real-world network traffic data. Well-fitting models were then put forth as appropriate to use. For this paper, the network histories of 24 wide area networks were collected and separated into 2 sets by network protocol. TCP connection traces and TCP packet traces were separated. There was a large amount of data collected to support this paper, including, but not limited to, 17 hours of traffic history between the UK and the US, and 13 days of Belcore traffic history. When I was reading this paper, I thought it seemed very fair and well-reasoned in its conclusions, and it does not have any significant form of bias I can spot. We are meant to learn from this paper that different types of network trafficking cannot be assumed to fit one model. Additionally, the patterns seen in wide area networks are influenced by a variety of real-world factors which should be taken into account when modeling traffic data. We now know Poisson network modeling was overextended in its usage of modeling different types of traffic data. And thanks to this paper, we can now correctly model telnet, multiplex TCP, and all protocol traffic. When the authors tested models to fit FTP traffic, a model was not found that fit. Additionally, there were no attempts made to model or disprove telnet responder traffic was Poisson. No hypothesis was given on what type of model would fit telnet responder traffic. The authors predicted any future model for FTP traffic should focus on the tail, the occasional traffic burst. In 2005, Gerald Martin published a paper on how to model FTP traffic using a combination of mathematical functions, which were based on exactly what the authors predicted. This paper is logically sound, and it makes sense how the authors came to the conclusion the Poisson model needed to be replaced for some types of traffic. Their line of thinking was, if the new model fit the data better than the old model, then reject the old model. While there was a large amount of data collected for each sample, there were not a large amount of samples taken. The sample group had a size of 24, and we needed to exceed a size of 30 to be considered a large sampling group. However, all of these network histories have thousands and sometimes millions of individual elements. I am concerned about the amount of data collected from two of the networks. Between them, 20 of the 24 network histories were obtained, and disproportionately large amounts of data came out of these samples. There was one assumption in the paper the author acknowledged was a bit far-fetched. Accessing directories and transferring the files were approximated to Poisson and were presumed to be self-similar when modeling FTP traffic. However, the spacing of arriving FTP data connections were shown not to be Poisson earlier in the paper. Since the author only used this data to show FTP was not Poisson, I don't think any issue with the set of assumptions in this session. Before I discovered a model for FTP traffic was found in 2005, I played with the idea AI could be used to find a model. While this does seem extravagant, there'd be no practical use for such a model. First, there already exists a mathematical model for FTP traffic. And if AI was to come up with a model, it would only give a closer approximation to that. Secondly, FTP traffic has many security issues and has fallen out of use. Additionally, FTP traffic is no longer being updated by a support team. AI may have not been tried for a variety of reasons. The worst point of the AI winter was during the original publication date of the paper in 1995, and a mathematical model was found 10 years later in 2005, 7 years before the AI winter ended. Overall, this is a very well done paper. If I had to make a suggestion, I would say to use a larger and more diverse set of network histories so that the data is not skewed by a small amount of network patterns, and so the same sample group can be assumed to be normally distributed.